Green chemistry. Of water and land occurred. This led to increase in rate of many life-threatened disease like cancer. Thus green chemistry came into play. Paul Anastas is widely known as father of green chemistry, for his work on the design and manufacture of chemicals that are non-hazardous and environmentally benign. Green chemistry, also called sustainable chemistry, is an area of chemistry and chemical engineering focused on the designing of products and processes that minimize the use and generation of hazardous substances. Whereas environmental chemistry focuses on the effects of polluting chemicals on nature, green chemistry focuses on the environmental impact of chemistry, including technological approaches to prevent polluting and reducing consumption of non-renewable resources. Principles of green chemistry. One. Prevention. It is better to prevent waste than to treat or clean up waste after it has been created. 2. Atom economy. As the substance produced is eco-friendly, so the procedure to process it should be not hazardous to mankind. 3. Less hazardous chemical synthesis. Wherever practicable, synthetic methods should be designed to use and generate substances that possess little or no toxicity to human health and the environment. 4. Designing safe chemicals. It says that green chemistry aims on making substantial progress in making chemicals which are effective when retained or exhausted but less toxic.
Principle 5. Safer solvent and auxiliaries. The solvents and auxiliaries, drying agent, blowing agent, etc. used in chemical synthesis will become part of the wastes. They may cause environmental pollution and health hazard. 6. Energy efficient. It focuses on that prospect that energy requirement should be minimum, which can be done by making the process at ambient temperature, i.e. not to high temp and pressure. It makes the process more viable. 7. Use of renewable feedstocks. Use of raw material should be done which is renewable in nature, and if not, then recycling of that material should be done at maximum extent. Reduce derivatization. Unnecessary derivatization should be avoided if possible because such steps require additional reagent. Principle 9. Catalysis. Catalysis reagent are superior to stoichiometric reagent. In stoichiometric reagent, every mole of product, which catalytic reagent, carries out thousands of transformations. 10. Design for degradation. It should be in such a way that when the products are formed, then the latter part should not persist in environment and cause to it. It should be biodegradable. 11. Real-time analysis for polluting. Real-time analysis is essential for better efficiency and safe operation. In green chemistry, it requires real-time, in-process of monitoring techniques coupled with process control. Inherently safer chemistry for accident prevention. In green chemistry, as here, we do not use hazardous substances which causes harm to the nature, as well as humans, then the percentage of a happening tends to 0, which is a good sign. Synthetic method. A. Preparation of acetanilide. B. Nitration of phenol. C. Bromination of acetanilide. Acetanilide. Green preparation. When aniline reacts with acetic acid, then it forms acetanilide. Acetanilide. Commercial preparation. Acetanilide, when reacts concentrated HNO3 with temperature below 20 degrees Celsius, forms para-nitroacetanilide as major product. When phenol is reacted with 20% HNO3 at 298 Kelvin, then the products formed are orthonitrophenol and paranitrophenol. This reaction. When HNO3 reacts with H+ as catalyst, then intermediate is formed, and due to removal of water, it forms NO2 cation. When this cation reacts with phenol, an intermediate is formed, and deprotonation leads to ortho and para-nitrophenol. Bromination of acetanilide. When acetanilide reacts with glacial acetic acid, then para-bromoacetanilide, along with ferric bromide and HBr, is formed. This reaction. Why green chemistry should be used? Firstly, avoid use of acetic acid. Secondly, minimize the waste byproducts. Thirdly, avoid hazardous substances. Use of acetic anhydride. Question 1. Why is the use of acetic anhydride banned? Question 2. Why is acetic anhydride dangerous? Question 3. Is acetic anhydride toxic? Acetic anhydride is banned in many countries because it is used as the major precursor for the production of heroin, and is also used in manufacture of improvised explosive devices. Corrosive chemical, and contact can severely irritate and burn skin and eyes with possible eye damage. Breathing acetic anhydride can irritate the nose, throat, and mouth. High concentrations can cause severe lung damage with coughing or shortness of breath. Is acetic anhydride toxic? The substance decomposes on burning, producing toxic fumes including acetic acid fumes. It reacts vigorously with alcohols, amines, oxidants, strong bases, and water. Minimize waste byproducts. Effective processes and policies occupy the hierarchy of waste from the top. This term is strongly taken with all the efforts made to have the minimized use of energy and resources. When we speak for waste minimization, we know that fewer materials are utilized to manufacture products at industrial level, consequently, lesser waste is produced. The waste minimization is not an easy task to comprehend, rather extensive knowledge is there waiting to be revealed. Hazardous substances. This can lead to many diseases that can be harmful to the human health. Asthma, a result of developing an allergy to substances used at work. Losing consciousness, a result of being overcome by toxic fumes. Cancer, likely to appear long after the exposure to the substance that caused it. Viral infection caused by bacteria and other microorganisms, biological agents. It is self-explanatory. It shows symptoms of asthma and shows how cancer cells have uncontrolled growth. It also shows what is the difference between bacteria and virus and similarities between them. Q.